Hello, my name is McGuire Hodson, and this is my lab report for Lab 2, Magnetic Field of a Bar Magnet. The purpose of this lab is to explore the magnetic field of a bar magnet using an experiment and to compare these experimental results with a computational model made using VPython. The magnetic field is visualized using a magnetometer app. This lab is based on the dipole model of magnetic fields, which states that B is equal to mu naught over 4 pi times 3 mu times r hat minus mu vector over r hat cubed. Based on the results of the experiment, the magnetic dipole moment of a bar magnet was found to be 25.05 angstroms times meter squared. This closely matches the computational model. A computational model was made for this experiment and included the data after collecting it. In this model, the bar magnet is treated as a magnetic dipole, so the corresponding equation for a magnetic field is used. This system is the bar magnet and its magnetic field, while the surroundings are the objects and Earth's magnetic field outside of it. The assumptions for the model are that the magnet behaves like a point dipole, that the magnetic field is calculated in free space, and that there are no external magnetic fields in the surroundings. This model is an appropriate approximation of the magnetic field created by the bar magnet and is a useful visual tool. This is some of the relevant code for the computational model, and this is just a stock image for the magnetic field. In this experiment, the magnetometer is aligned with the magnet's axis based on Earth's magnetic field. The bar magnet is then placed on a tape measure aligned horizontally while the magnetic field is measured. Each magnetic position is measured in meters, and magnetic flux density is measured in teslas, these both being the scientific units. The magnetic field of exterior objects in the surroundings, aside of course from Earth's magnetic field, is ignored. Earth's magnetic field is controlled for on the x-axis. Magnetic position and flux density are measured at various distances, and data is collected 3 times for each measurement. After the magnetic field of the bar magnet is measured, the off-axis field is also determined using perpendicular movement instead of parallel. So this is an image of the experiment setup. After collecting the data, the magnetic dipole moment was found to be 25.05 angstroms times meter squared. As expected, the magnitude of the magnetic field decreased significantly as the magnetometer moved farther from the bar magnet, approaching zero. Along the positive axis, the magnetic field was found to point in the same direction as the magnetic moment vector. Along the y-axis, in the perpendicular direction, the magnetic moment points in the opposite direction. Both of these are expected. The position of the magnetometer has a large effect on the measured x component of the magnetic field. And the results of the computational model showed the magnetic field vector at a 45-degree angle to be the vector 3.33 times 10 to the negative 4, 1.35 times 10 to the 4, 4 times 10 to the negative 5 teslas. So this is an image of the results of the computational model with the magnetic field vector pointing 45 degrees to the right. And then these are the results of the experiment. So this is the data for the first part with the graph that was made in Excel. And this is the results for the second part of the experiment. So the model predicts that the magnetic field strength increases as the magnetometer gets closer to the dipole, which is consistent with the experimental data. The predictions from the model were similar to the real system, but there were some differences. For example, the model used the dipole magnetic field equation, which deviates from the actual magnetic field. Other differences were from error sources, including difficulty aligning the magnetometer with Earth's magnetic field and an imperfect calibration of the phone sensor. If magnetic north was not compensated for, the magnetic field would be much more skewed and the magnetic moment would be inaccurate, especially in the x direction. If 2 magnets were used end-to-end, the magnetic dipole moment would be doubled and the magnetic field would be about twice as strong. Despite some experimental errors, the computational model and data collected provided a useful approximation for the magnetic field of a bar magnet.